principle of moments tells us that if an object is in equilibrium, then the sum of the clockwise moments on the object is equal to the sum of the anti-clockwise moments on the object. In other words, if you add up all the moments that are trying to turn the object clockwise and you add up all the moments that are trying to turn the object anti-clockwise, then these two totals will be the same. So this is the second condition for an object to be in equilibrium. The total force on the object has to be 0 and the total moment on the object has to be 0. The principle of moments allows us to answer questions like these. Now, often you need to make a sensible choice of point here. So which point are you going to find moments about? But in this question, they've done it for you. So they're telling you that the point is going to be here, the point that they've labelled pivot. Okay, pause the video and have a go at this one. Okay, so this is an example of a question where the forces have angles marked, not perpendicular distances. So let's start with the force F. If I draw from where F is actually acting on the person, and I draw down to the point that we're interested in, there we go. So that D there, that displacement is the 25 centimetres. Okay, so I'm going to say, so for F, the displacement is 25 centimetres. Okay, and then for the W acts on the person here. Unfortunately, I don't have another highlighter, so acts on the person here, and so here is the D arrow for the weight force. So that D there is 40 centimetres. Okay, and so putting those numbers into our formula, we've got the total clockwise moment is just the moment due to F. We've only got one force trying to turn the person clockwise, so that's the moment due to F is F, size of F, times the size of the displacement vector, times the sine of the angle between them. So there's F, and there's the displacement vector for F. So the angle between them is 15 degrees. And then the total anti-clockwise moments, well, there's only one force trying to turn the person anti-clockwise, and that's W. So we've got the size of W times, and then there's the displacement vector for W. So that's 40 centimetres long. So size of W times size of the displacement vector times sine of, well, if that's 30, then there's my displacement vector, there's W, so the angle between them's there. If that's 30, then this one is 60 degrees, so sine 60. Size of the force times size of the displacement times sine of the angle between them. And so that gives us, to two significant figures, 2,400 newtons. But sometimes the question doesn't tell you where to choose as your point, and then there's a trick to it. Basically, you need to choose a point where there's a force going through it, and it's a force that you don't know and you're not interested in. Okay, so if you would like to have a go yourself, pause the video and have a go at this question now. Okay, so first of all, what they're looking for this question here is just for you to say that the object is not uniform. It's got more mass at the front than the back, and that's why the weight doesn't act through the middle. And then the next part of the question is asking me to show that the force B is 64 newtons by using the principle of moments. Now in this question, we do have the perpendicular distances marked. That makes sense once we've actually chosen the pivot. So here we've got a force B that we're trying to work out, W that we know, and then A That is the force the second person is exerting, and we don't know what that is, and we're not asked for it yet. So where are we going to choose as our point? We're going to choose here, because A will have no moment, will cause no moment about this point, and we can therefore ignore it. Why does it cause no moment? Because the distance is 0. The distance between the force and the point is 0. Okay, so this is going to be our point. And so if I draw in my distance from the weight to the point, we can see, so I know what that is, that's 20 centimetres, and we can see that it is a right angle. So the 20 centimetres is the perpendicular distance. And then there's my W over there. Now, I don't know how you want to do this one. I think the easiest thing to do is to recognise that here, again, we know what this distance is. Okay, so if I was to continue the line of B down there, that 110 centimetres is, switching to the highlighter, there. And you can see that that has a right angle between the two lines, and so that is the perpendicular distance again. And so this time our clockwise moments, again we've only got the one force trying to turn it clockwise, that's the weight. So we're going to have the weight times the perpendicular distance. Weight times perpendicular distance equals, the only force trying to turn it anti-clockwise is B, and there's the perpendicular distance, so B times the perpendicular distance. And then you put your unrounded answer there, because that's what they're looking for on the mark scheme, because it's a show that question. And then the last part of the question is a very common add-on. It asks you to determine the unknown force. And this is now a simple forces question. Here's a simple diagram of my lawnmower. I've got a weight force downwards of 350 newtons. I've got the force B upwards of about 64 newtons, and I've got the force A upwards. Remember, this is two people lifting it at either end. So that force A upwards is what I'm looking for. I know that the lawnmower is in equilibrium, and that means that the total upwards forces have to be equal to the total downwards forces. And so I get, when I've got the right weight there, A is 286 newtons.